We are talking about logs and exponentials, and I thought maybe it would be fun to tell you a true story from my personal life when I used logarithms. Have any of you ever actually used logarithms in your real life? I don't want to get too personal with you here, but I'm interested to hear. Like I can remember being, like a kid in middle school and high school, and people, I'm not sure I was ever this kind of kid, but people would often ask the math teachers, like, when are we ever going to use this in our real life? And I would say in high school, my answer is like never. Basically, I feel like the math which is useful in real life, you probably already knew when you were in like 5th grade or something. I don't know. Do any of you have like a story when you actually used high school math in your real life? I have added fractions in my real life. So I like to cook things. So sometimes I guess that's more multiplying fractions. Sometimes I want to scale up the recipe or something like that. Have you?
I used to when I was bored at work. I would like figure out exactly how much I was making per second as like a motivator.
Okay, all right.
That's like, it's not very complicated.
That's kind of, yeah, it's like multiplying and
fractions,
dividing.
Taxes.
Oh, the taxes, yeah.
That's
I suppose
what
there
really bored at work.
Uh-huh. All right. Well, thank you for sharing this personal story. Yeah. There's actually one time in my life. So I've been alive longer than you have, so I have more sort of material to work with. But there was one time in my life when I used the Pythagorean theorem, and there was one time in my life when I used logarithms. I will tell you the story of when I used logarithms in my real life. This is a true story about me. I have a genetic disease, a genetic disorder called hereditary hemochromatosis. Any of you guys have hemochromatosis? Anybody know what that is? It's a hemochromatosis. Yeah, it is a blood disorder which causes iron overload. So there is a natural thing that happens in your bloodstream which expels excess iron from your body. And if people with this genetic disorder, this mechanism by which iron leaves your body does not work properly for me. And the effect of that is that iron accumulates in my body, which can have damaging effects. This happens very slowly. So typically people don't know that they have this until they're like in their 60s, and then like their organs fail and they die. You can tell you have this. One of the symptoms is like your legs turn orange because actually like your legs turn orange because there's rust appearing in your skin from all the extra iron that's in your body. But anyway, hemochromatosis exists, like it's a genetic disorder which exists for the most part only in like Northern European white people. So, Fairfield University could be a hotbed for, if I must say. Yeah, like Northern European white people, about 1 in 40 white people is a carrier. It's like a recessive genetic trait. So probably at least one of you all is a carrier of this. You have no symptoms, but if you have a kid with someone else who is a carrier, then there's like a 1/4 chance that your kid would have it. And I, by some miracle, both of my parents actually have hemochromatosis, so I was guaranteed to have it, which is very unlikely that they both would. But anyway, yeah, it's a iron overload. It's worse in men than in women. Anybody want to guess why? There is a natural process, which we don't need to get into the details. There is a natural process by which women lose blood, and this causes a loss of iron in the bloodstream. So the effect is less for women. But for older women, they can experience the symptoms. Anyway, like I found out that I had it when I was fairly young, because I had some random blood tests that tested my iron, and they were like, your iron is way off the charts. So then I had the you can get a genetic test to tell if you have it or not. But anyway, when I first found out that I had this, so here's my logarithms story. When I first found out that I had this, there's a kind of blood test that you can take which measures, so what they measure in particular to keep track of this is called the serum ferritin level. And I guess this is just like extra iron that's hanging around in your blood. And the healthy level, like probably all of you, your level of the serum ferritin is around 20. This is very small amounts, nanograms per liter. That's very small, but that's the typical level of extra iron in blood of an ordinary, healthy person. My level when it was tested was 800, which is a lot more. I guess the like baseline levels could be anywhere from like 0 to 50 is sort of normal. 800 is way abnormal. And so anybody, there is a treatment though. So like right now, if you tested my ferritin amount, it's not super high. It's like probably in the 50s now. I know because I have to do this treatment every so often. There actually is there's not like a pill you can take that will destroy the iron in your body, because iron is an element, right? It can't be destroyed. Your body without like a nuclear reactor or something. So your body, the only way to get rid of it is to remove the iron from your body. And the way to do that, the simplest way, is just to remove the blood from your body. So they call this, the treatment is phlebotomy. This is like one of the only things that, like in the old days, they used to use leeches to cure you. This is like one of the only things where that would have worked. The treatment is basically I go and give blood and they just dump it in the trash, and that's the treatment. So every time I give blood, I lose a certain percentage of the blood in my body, and automatically I lose that percentage of the iron in my body. And if you do that enough times, that's how I maintain the level where it is. All right, so here's the math of this. So each phlebotomy, all right, phleb, reduces, like for me, the typical like blood donation, like the little bag of blood that you give, represents about 10% of the blood, all the blood in your body. That's about how much that is for an adult man such as myself. So each phlebotomy reduces the blood by 10%, and then your body will like regenerate. Your blood comes back, but the iron doesn't come back, again because iron is an element. Your body can't make it. The only way you get iron is by eating it. And so I have been instructed to eat less iron-rich foods. Like I cut out the horse livers or whatever. Like things with a lot of iron are not really good for me to eat. But anyway, each phlebotomy reduces the blood by 10%, and so it also reduces this serum ferritin, which for me was 800. It also reduces the ferritin by 10%. All right. So when I found out that I had this, the doctor explained all this to me. You're going to have to go do this blood thing every so often, like forever. And naturally, my first question was, how many times do I got to do it to get my level down to the healthy level? So this is the specific mathematical question. How many phlebs to go from 800 down to 20, right? Specifically. Each time you do it, the amount reduces by 10%. And so I want to know, you can reduce it 10% each time. How many times you got to do it to get down to 20? Right? This is the idea. What does this have to do with logarithms? Maybe you can, I don't know, can you see where this is going? So I'm going to say, let's say like f of, I'm going to write this as a function, something like f of k represents the ferritin level after K different episodes of this phlebotomy. All right, so F of 0 is 800, because that's the, when I didn't do anything, I was at 800. Can anyone say, what's F of 1? Maybe after I do it one time, what should it be? 720. Yeah, how did you get that?
10%.
Yeah, it's 10%, but you take away 10%, right? So this is 720. That comes from 800 minus 10% of 800, right? And then F of 2, you would subtract another 10%, which would be minus 72, whatever that is. 720 minus 72. All right. Another way, a better way of thinking of that, rather than 800 minus 10%, an easier way to think of that would be, instead of you get the whole thing but you take away 10%, it's easier to just say 90% of 800, right? This is a little simpler. So to do the math, it's just 0.9 times 800, right? So each time you do it, you're going to multiply by 0.9. That's the same as take away 10%. It's just easier to say multiply times 0.9. So F of 2 then would be this same answer here, but multiplied again times 0.9. And the way you could write that would be 0.9 squared times 800. Right? Isn't that cute? So generally speaking, can we say like F of t? Can anyone give me a formula for that? Yeah?
0.9 to the t times 800.
Yeah, 0.9 to the power t times 800. And now maybe you can see that logarithms might be useful to analyze this. So what we have an exponential function here with the base other than e. And can anyone say, how would I set up my original question? How many phlebotomies is it to go from 800 to 20? It has to do with this function somehow. Yeah?
You'd set 20 equal to the function?
Yeah, right. So we want 20 to equal this, 0.9 to the power t times 800, and then solve for t. This will tell me how many times do I need to do it in order for this quantity to reach 20, right? And how do you solve for t? This is where the logarithms come in. First, I would divide by 800 on both sides. 20 divided by 800. I did not simplify that on my paper. It would say 0.9 to the t equals 20 over 800. And now to solve for t, you must use a logarithm. There really isn't any other way to solve for t in this case. There are a few ways of saying it, but I would say, the way I usually think this through, take the natural log on both sides, just because I like the natural log. ln of 0.9 to the t equals ln of this stuff. And then what was the point of that? What can we do with this? Yeah?
Bring the t out.
Bring the t out to the front. And this is the key step, really. Now t is no longer inside the exponent. And now there's no problem to solve for t. If you have a calculator, you can do those other logarithms and then solve for t. So this t is ln 20 over 800 divided by ln of 0.9. And all of that you can just plug into your calculator. And I did this. I got 35.01. That means you have to give blood 35 times in order to get back to a healthy level. Isn't that cute? This is the only time that I've ever used logarithms in my own life. I suppose I didn't really need to know the answer to this question. I could have just done it. But I asked the doctor at that time, like when I first talked about him, I don't know how surprising this is. I had more or less thought all of this through immediately when he told me what the treatment was. I was like, oh yeah, that's going to be an exponential function. And but I asked him, like, how many times do you think I'm going to have to do it to get back to the normal level? And he said, probably you should do it every 2 weeks for a year, which is kind of close to that. That's a little bit. This is a little bit more. Ordinarily, you're not supposed to donate blood that often, but like, if you have a medical reason, then let it flow, they say. All right. So this is my personal tale. Any thoughts about that? I thought it was interesting. That was a while ago that I was doing it very often. Now I do it like every couple months just to maintain the ordinary level. and they don't just throw it away. It was kind of demoralizing. Like, they would just take my blood, and because my blood had so much iron in it, they would just like right in front of me dump it in the trash. It's like, yeah. I also have to, like, the people who treat this kind of thing are hematologists, which are blood doctors, and almost every hematologist is doing leukemia treatment. Like, that's what most blood doctors do, because there aren't that many blood disorders, I guess. So I, like, when I do all of these things, I do it at a local cancer center, and people in there always think that I have cancer, and it's awkward to, like, I come in and they, you know, when you get there, they like do your blood pressure and your height and weight, and they're always like, man, you look great. All right. And they have like snacks. It says like, you can do this, take a cookie or something. Yeah, I'm doing it. It's weird. All right. Let's discuss, okay, so logarithms with other bases. That's what we're talking about. That's why I mentioned all that. I would be happy to share with you the time that I used the Pythagorean theorem in my real life at another time. So I believe last time we mentioned at the very end this formula, which I hope everybody remembers. The derivative of a exponential function of a different base, b to the x, is b to the x times ln b. I think that's the last thing that we said last time. And this naturally, so it says if you take the derivative, you get the same thing again times this extra bit. But this extra bit is just going to be a constant, because you have to imagine I'm talking about something like 2 to the x or 0.9 to the x. And you just get an extra constant right here. When you take the derivative, you get the same thing times a constant. That automatically means if you do the antiderivative, you get the same thing but divided by that constant. So sort of for free, we get this formula. Integral b to the x dx is the same thing again, but you divide that same constant. So it's 1 over ln b, b to the x plus c. So these are kind of the formulas for derivative and integral. I'm not afraid to admit it, I have never used the derivative or the integral in my real life, I think. What's the point of learning it? I would say, like, our whole modern world is built on calculus. So I use technology all the time without even thinking about it that uses derivatives and integrals. But I personally have never had the occasion in my own personal life. All right, these are the formulas you should know for exponential functions with a different base. All right, what I would like to talk about today, at least part of today, I don't know if this will take the whole time, is logarithms with other bases. Last time we talked all about exponentials with other bases, but not logs with other bases. So let's get into that. Logs with other bases, all right? Remember, our whole setup here is we started with ln of x, and the inverse of that is e to the x. So I'm going to say, y equals e to the x is a function, and it is the inverse of y equals ln x, where ln x is defined in terms of some slightly weird area under the curve of 1 over t dt. All right? And last time we discussed y equals a to the x. This is also a function. Actually, I usually call it b to the x. I might as well stick with b, although it doesn't matter. Y equals b to the x is a function. Anybody recall the definition of that? So this was not defined as the inverse of something or other. It was... Anybody remember? This is a slightly weird definition of b to the x. Yeah?
E to the x ln b.
Yeah, right. B to the x is defined as e to the x ln b. The reason for making this somewhat weird definition of an exponential is just because it's not clear what that's supposed to mean if x is not a whole number. They're very weird considerations. And this is a way to get around all of those weird considerations. ln is what it says up there. Okay, so e to the x is the inverse of the natural log. B to the x is a function which is, we haven't defined it as the inverse of anything. But what is it the inverse of? Well, that's what the logarithms with other bases are. So this function, which we call log base b of x, is defined to be the inverse of b to the x. All right? The log with base b, that's how you say this log with a little b, is defined to be the inverse of b to the power x. All right? And this actually is probably how you've seen this definition before, like in high school. This is usually how it's presented. That this, what this logarithm means, it means the inverse of b to the x. Although it's a little weird. We started with ln, then the inverse of that is e to the x, then you make b to the x, and the inverse of that is log base b of x. Somewhat strange. All right, so what that means, let me just say in other words. So if I have a specific y equals b to the x, this means another way of saying the same thing, to say it the other way around in terms of inverses, it means log base b of y equals x. All right? Because the log base b is the inverse of that other thing. So it means you can rewrite the same formula the opposite way around using the inverse, which in this case is the logarithm with base b. All right? And sometimes when people write sort of these two things, this is the exponential format, and this is the logarithmic format. They both represent the same thing. They're both saying the same thing, just written in two different ways around. All right? What that means is you can use this basic setup to do a lot of logarithms kind of by hand or in your head. You know, most of the time if I ask you to give me the log of something, you just use your calculator. But some things you can do sort of in your head. So how about do these by hand? Log base 2 of 8 equals. How do you figure out the log base 2 of 8? I would suggest write this in, so this as written right now is in the logarithmic form. Can I translate that into the exponential form? The exponential form would rearrange this, so instead of putting a log on this side, it puts an exponent on this side. It would say 8 equals 2 to the, right? That's the same thing, but just written in the other way around. And now you should be able to guess the answer. What do you say? 3, yeah. 2 to the 3 is 8, all right? So here, just a little narration here. Now we can see it's 3, all right? So that's why log base 2 of 8 equals 3, all right? Drink up. I don't think you heard me. Okay. This only works in very particular examples, though. Like this is log base 2 of 8. If I had asked you, okay, then what's the log base 2 of 9? Your answer is, I don't really know. Because if you said log base 2 of 9, that would convert to this, which would say 9 equals 2 to what power? And the answer is, I guess, like a little bit more than 3, but there's no way to tell without using your calculator in that case. All right, how about some other ones? Here's a little trickier. Log base 4 of 16. This is not really trickier. Equals. What do you think? So one way to rewrite this. This says 16, by the way. This I could translate into 4 to what power equals 16, right? What do you say? 2, yeah. So this is log base 4 of 16 equals 2. Great. How about, that was not really a terribly difficult one. How about this? This is introducing a slight complication, but actually you can do this one in the same way. log base 4 of 1 over 16. All right, this again would translate into 4 to what power equals 1 over 16? Negative 2. Yeah, when you see this fraction over here, you should start thinking, I'm going to have to use a negative exponent because that's what negative exponent means. It means you make a fraction. So 4 to the negative 2 would be 1 over 2 to the 16. So this equals negative 2. That's because, if you want to know why, that's because 4 to the minus 2 equals 1 over 4 squared, which is 1 over 16. So that logarithm is negative 2. All right, what else? I got just two more, just one more. How about log base 7 of 1? Equals, huh? Can someone say, how would you write this in the exponential form? Something to the,
1 equals 7 to the x. Or did I do it backwards?
Yes, yeah, that's right. 1 equals 7 to what power? And it's 0, yeah. 7 to the power 0 equals 1. That's what 0 power means. So this right here, log base 7 of 1 equals 0. And that's because if you want to tell your friends, since 7 to the power 0 equals 1. And this is, of course, not a special property of the number 7. This is true for any number, that anything to the power 0 equals 1, except for 0, but we don't want to get into that. Generally speaking, the log with any base of 1 is always 0 for any base b, where, of course, b has to be greater than 0. Like, there are problems. We never talk about bases that are negative because, well, we've discussed in the past that that can cause some issues. You'll get imaginary numbers, which I don't want to deal with. All right. I hope that this is familiar to everybody, but I just want to make sure we're all on the same page. One important property of the logs with other bases that you've probably seen before is what they call the change of base formula. And this is so common that it's worth knowing about. The change of base formula. This is how you can reconcile, or how you can relate a log with a certain base is related to the log with a different base. And the way that that works is, I will try and set this up. If I have something like y equals log base b of x, that, of course, is the logarithmic form. I can rewrite that in the exponential form. It would say, what would that say in the exponential form? That is, you write it the other way around using exponents. Yeah?
b to the y equals x.
B to the y equals x. Yeah, right. B to the y equals x. All right? And I would like to know how this log relates specifically to the natural log. That's usually how they write the change of base formula. One log in a weird base can be expressed in terms of the natural log. And towards that end, I'm going to do ln on both sides here. All right? So it will say ln b to the y equals ln x. And then I'm going to do my favorite property of the natural log, which is that y in the exponent can come down to the front. Y ln b equals ln x. And then you can solve this for y, and we have the change of base formula. So this says y equals ln x divided by ln b. And of course, I hope you remember, at the very beginning, I said y is the log base b of x, right? So that means, just putting y back in, log base b of x is the natural log of x divided by the natural log of b. This is the change of base formula. This is not a formula about derivatives or anything. This is just straight up what it is. This log base b of x actually equals this over here. And this is why, like, a typical calculator doesn't have a log base b button on it. If you want to do a log base b, you are expected, as a responsible calculator owner, you are expected to already know this formula. And you do it using natural logs. All right. This formula is also true if you use the base 10 log, which is also called the common log, written log without a little number down there. I'm not into the base 10 log, though. All right. That means, so the moral of this story, this is kind of what I just said, is that all other logs can be converted to ln's, right? Using that formula right there. If you're ever dealing with some other logs and you don't like it, you can switch them to all natural logs if you prefer. All right. One last thing to say about these other logs. I think really there's not much to say about them at this point, but there is a formula for the derivative of one of these other logs. So let's discuss. What about derivative? I want something like this. I'm gonna fill in the box. How would you take this derivative? Even if you don't know what the answer is already supposed to be, you can use the change of base formula up there. So we can work this out by changing the base. Work it out. If I have derivative of log base b of x, this is the same as derivative of ln x divided by ln b, right? That's the change of base formula. And keeping in mind that this ln b is a constant, right? B is just some specific number. And so this ln b is a constant, which means I can remove it from the derivative. So this can factor out 1 over ln b derivative ln x, right? And what is derivative ln x?
1 over x.
It is 1 over x. And that's really all there is to it. 1 over ln b times 1 over x. That's it. So this is the derivative. So in the box, usually this is written like this, 1 over x ln b. But that's where it comes from. All right, this is the derivative of the log base b. So you will want to use that formula every so often. Any questions about that? I think this is not something we need to talk a whole lot about. All right. One more thing to say concerning logs and exponentials and all that, which we've been talking about for maybe a week or so, a little more than a week. I would like to talk about one last thing, and that is, what about the number e as a limit? We have basically, by this point, sort of talked about all the stuff that you are likely to know about logs and exponential functions and the number, e to the x and whatever. But this is one thing in which we haven't mentioned. And I said, part of the reason to define logs and the exponentials in a slightly weird way in our book is to avoid talking about the number e as a limit. But we should be able to also demonstrate the number e is equal to some kind of weird limit. And this is usually how this number is presented, like to typical kids in high school. They usually define e as this. Limit as x goes to 0, 1 plus x to the 1 over x. Or sometimes these are equivalent. The limit as x goes to infinity of 1 plus 1 over x to the power x, right? And actually, historically speaking, this is the original way in which e was sort of invented, or the first people who thought about the number e. They thought of it in this way, not in terms of being the inverse of a logarithm, because they didn't know, there was no such thing as logarithms when they started talking about e. So what about the number e as a limit? Can we figure out how to demonstrate that e really is equal to these limits over here? It's not so hard based on the stuff that we already know, and I think this is a cute little example of using the stuff that we've learned already. So to us, the definition of e is defined as the natural log of 1, right? That's not true. I wrote it backwards. E is the number where the natural log of e equals 1. The natural log of 1 is 0. We just talked about that. It's written backwards on my paper. Sorry. Don't tell anyone I said that. It's not true. E is the number with natural log e equals 1, right? That, for us, that's the definition that we used for the number e. So can we demonstrate that this number, using this definition, is actually equal to this somewhat strange limit up here, all right? And actually, it comes from, in some sort of strange roundabout way, all of this comes from the fact that the derivative of ln x is 1 over x, all right? So it comes from that derivative formula, and I'm going to write this, so let's call f of x, just so I can talk about this as a function. F of x, I'm going to call ln of x temporarily, and then f prime of x is 1 over x, and so f prime of 1 is equal to 1. Sorry, I'm looking carefully at my notes here because I'm not sure. Yeah, this is going to be fine. Sorry, I made a typo and I'm making sure it's not also wrong here. Okay, so f prime of 1 is 1. All right, but here's a little something that I think maybe we haven't done yet in this class. We can also, this is something we are not really going to do otherwise in this class, but we can also find f prime of 1 using the definition of the derivative. The definition of the derivative. This is the thing about the limit as h goes to 0 of something, something, something. Do you remember that thing? Which you never want to use again after you learn like the tricks for doing the derivative. But that would be f prime of 1 is lim. Anybody actually remember this? How it goes? Yeah?
F of x plus h minus f of x over h.
Yeah, so it's going to say, so he said f of x plus h. I'm going to use 1 because I'm only really interested in f prime of 1. So f of 1 plus h minus f of 1 over h. This is the formula, the definition of the derivative, all right? And if we actually plug this business in, you know, I hope you remember how to do these. We're not going to do any examples like this in this class, but the way to evaluate this limit here would be, first I would say plug in for the f. This f means ln. So this says, oops, it's still lim, h goes to 0. It says ln 1 plus h minus ln of 1 divided by h. Can we do anything to simplify in there? There is one thing you can do. Yeah?
ln of 1 is 0.
Yeah, ln of 1 is 0. So that can go away. Otherwise, actually, you can't really do much with this. It will say lim h goes to 0. ln of 1 plus h divided by h. Would you mind if I write 1 over h times ln 1 plus h? All right? And I'm going to do one more weird step, which really there's no good reason to do this last step that I'm about to do, except in this particular example. I'm going to use my favorite property of the ln, but backwards. So the coefficient of 1 over h can move inside the log and become an exponent. So this will say ln 1 plus h to the power 1 over h. All right? Okay, and all of this equals f prime of 1, right? That's what I started with. And you can still see at the very top of the screen, f prime of 1, we've already said, is 1. Because that's 1 over x with 1 plugged in, so it's 1 over 1. So my conclusion is 1 equals this limit, ln 1 plus h to the 1 over h. All right? What this means is these numbers, when you take the limit, the log of these numbers approaches 1. All right? And what that means is there is only one number whose log is 1. If the log of these numbers approaches 1, it means these numbers themselves approach e. E is the number which is the one that makes the log equal to 1. All right? So that means these individual numbers without the log must approach e. If the log of them approaches 1, the only way that's going to happen is if those original numbers approach e. 1 plus h to the 1 over h equals e. And this is the weird formula for e in terms of a limit of something or other, which is, this is typically taken as the definition of e, but for us it can be derived from all this other stuff. All right? It's a little strange to write this with a h. I mean, usually people write this with a x, just changing the name of the variable. Lim x goes to 0, 1 plus x to the 1 over x. Right? That's what I was trying to justify. So even this weird formula for e as a limit of something or other can be derived using the logarithmic approach. All of this basically followed from this, the derivative of the log is 1 over x. All right. And here ends, I believe, all the stuff that I want to say about exponentials and logarithms. Any lingering questions about any of this? When are we ever going to use this in our real life? If you find out you have a white people blood disorder, you may use this once out of curiosity to see how bad it is. All right, great. This is the end then of section, I believe this is section 6.4 star about exponential and logarithms of other bases. And we are going to move on. I think this is 6.5. It doesn't really matter, but one last section which is generally on the theme of inverses. So we had this section just about inverse functions in general, and then we talked about logs and exponentials because they're inverses of one another. One other type of inverse functions that we need to talk about, this is something you may have seen in high school, maybe not, inverse trig functions. I think these are discussed in the typical A-B calculus, which I know some of you have seen that stuff before, some of you maybe not, and it's fine. I'm not going to assume that you've seen any of this. But these you will see buttons on your calculator like sine. This is like that thing, which we call inverse sine of x. This is called inverse sine. Or this is also sometimes called arc sine. Those are synonyms. I kind of like the arc sine name better, although our book always writes it with the little inverse thing, the little -1. Why I don't really like the little -1, because you just have to keep it straight here. This is not 1 over sine x, right? Even though that little -1 you might interpret as a 1 over, but it's not. It means the inverse, not the 1 over, not the reciprocal. All right. Of course, 1 over sine x already has a name. That's the cosecant of x. If you see this button on your calculator, sine with a -1, it doesn't mean the cosecant. It means, well, it means this, the arc sine or the inverse sine. All right. It means the inverse. That is to say, what is the angle that I would have to use to get sine of something equals x? That's basically what it means. But it's used for this. These are actually, they come up in the real world. I won't say in your own real life, but they come up in something like, I imagine that like carpenters or people who build stuff have to have a basic understanding of this. If I have a triangle and the side, I want these two sides to be, say, 1 and 3. What's the angle here? This question requires you to understand something about the inverse trig functions. All right. The ordinary trig functions usually are used in a situation where you know what the angle is, and then you use like the cosine of that angle is whatever, and that will allow you to deduce something about the sides. But if you know the sides to begin with, and you need to know what the angle is, then you have to use one of these inverse trig functions. In real life, you probably would just use like a protractor or something to find out what what the angle is. Have you ever used a protractor in your real life? You have? Not in real life. I mean, not like in a classroom. That doesn't count as real life. But yeah, I don't think I have ever used a protractor in real life. Yeah. I found a very nice quality antique brass protractor at a yard sale once. Never used it, but I have it. It's in my basement. All right. How could you actually figure this out? So in the case of this particular problem, let's call this angle theta. I hope you don't mind me using the Greek letters. All right. What's the angle? So this is some angle. This angle satisfies, in this case, given the information in this problem, you don't know what the angle is, but you can say, what is tan theta in this case? You have to remember your, yeah?
1/3.
Yeah, 1/3. The tangent is the opposite over the adjacent, and so in this case, tan theta would be 1/3. And so how do you find what the theta is? You use the inverse of the tangent. So in this case, theta, writing it the other way around with the inverse tangent of 1/3. And how do you do that? There's a button on your calculator that says that. This is the inverse tangent function, also known as the arctangent function. All right? And this is what it's useful for. So use your calculator. There's no way to do that by hand per se, but your calculator can do it. All right. There are big problems though in talking about even the inverse tangent. So this is a weird issue. I hope that everybody knows, in order for a function to have an inverse, it must be 1-to-1, right? The weird issue is sine and cosine and tangent. None of them are 1-to-1. And so technically speaking, they don't have an inverse. Another way of saying that is maybe there are many different inverse tangent of 1/3. Like this is a true fact. There are many different values of theta which give you tan theta equals 1/3. So there's a little subtlety that we have to think about. And this is true of sine and cosine also. I hope everybody knows the graph of sine looks like this. You can see immediately it's not 1-to-1 because for 1-to-1 you should be thinking about these horizontal lines. They hit the graph actually infinitely many times. That's sine. Cosine, of course, is similar, but it starts up here, right? Also not 1-to-1. And the tangent, I hope you remember, the graph of the tangent is something like this with recurring vertical asymptotes. But anyway, this is cosine, this is tan. None of them are 1-to-1. So we have to be very careful when we talk about these inverse trig functions and making the definitions properly. So that's what we're going to talk about for the next little bit. The issue is we consider only a piece of the graph which is 1-to-1, right? So the entire graph is not 1-to-1. So instead of using the whole graph, you just pick a specific piece of the graph where it is 1-to-1, and then that's the one that you use for all of your inverses. So let's talk about, I just want to talk about sine, and then we'll talk about cosine and tangent. They all go, in similar ways, but let's talk about sine first. So for sine, of course the graph, it looks like this. What? No, it goes through the origin. Like this, right? Can we choose a piece of this which is 1-to-1? So if you ask me, if you approach me in the club or something and ask me like, what's your favorite piece? Just pick a piece of it. To me, I usually pick like that. To me is like one piece of sine, and the rest of it is just repetitions of that. But actually even that is not 1-to-1, because if I do this horizontal thing, it still hits the curve twice. So that is not the piece that I'm going to pick. I'm going to pick some piece around the origin, which goes as far as it can in a way which is still one-to-one. Anybody suggest how much should I use?
Negative pi to pi.
Negative pi to pi.
I mean, sorry, pi over 2.
Yeah, negative pi over 2. That would be here to here. Yes. So that much of it, if I draw, that means from there to there, this part only. And you cannot go any further than that without introducing some sort of 2-to-1 points, right? You need to take a piece which is 1-to-1. If I went any farther, it would start to go down and it wouldn't be 1-to-1 anymore over here. And similarly over here. All right, so only this piece, of course, this goes from -1 to 1, right? So we use only, I'll draw this again slightly nicer. Only here, up to pi over 2, back to negative pi over 2, down to -1 and up to 1. That. It's supposed to go through the origin. That much. Only this. And this, so this is sine of x. It's a piece of sine of x at least. It's not the whole thing. That you can find the inverse of that. So its inverse is the same thing, but I mean, in terms of the graph, it would be reflected across this horizontal diagonal line, right? And so we are basically interchanging the x-axis with the y-axis. That means the labels that I'm going to draw on the x-axis are -1 to 1 because they have been interchanged here. So my x-axis goes -1 to 1. And the y-axis will be negative pi over 2 to pi over 2. Because I am interchanging the x's and the y's everywhere. And then the graph, again, it will go through the origin. And it will go sort of, from here to here, right? And through the origin. But it's this shape, only it's been reflected across this straight diagonal line. So it still has this kind of curvaceousness, but in the other way. So this one goes kind of flat and then up. Here I want to start going sort of up and then flattening out. So the graph looks like this. To begin with, that's a reflected version of this piece. It gets bumped out the other way. And then this one up here gets bumped down the other way. So it looks like that. All right? That is the graph. So this is the function inverse sine of x, also known as the arc sine of x. All right, and this graph here, you might wonder, like all of this was done by just taking a little piece here because you can't go any further here. Why don't you just keep going? I mean, it looks like this just kind of ends. Can't you just like keep drawing more of that function? I would say the only sensible way to keep going here would be to do something like this, right? It's like sine but sideways, but that's not allowed because that's not a function anymore because of the vertical line test. So that's why you cannot continue. All right. So let me just say some details about this. So sine of x. No, I'm talking about the inverse sine of x. This is called inverse sine, or it's also called arc sine, which I like a little better. It is a continuous function, but it has only a piece of the domain. So this is continuous. The domain is the closed interval -1 to 1, and the range is the closed interval minus pi over 2 to pi over 2. So what you plug into sine are like are ordinary numbers. They're not typically multiples of pi. So you would never, I mean inverse sine. You would never do like, what's the inverse sine of pi over 2? That is actually, that's not even part of the domain. The domain only goes up to 1. pi over 2 is more than 1, so you would never talk about inverse sine of pi over 2. You would talk about something like inverse sine of 1/2 or inverse sine of 1 over root 2 or something. Those are ordinary values. Actually, can we just talk about those values like that? So I'll say we can figure by hand some values. Most of the time you have to use your calculator, but we can figure out some values. For example, what is inverse sine of 1/2? All right? And I want to think of this similarly to how I was thinking about the logarithms by writing it in the other way around. So this equals, this is the same as, this is interchangeable with sine of equals 1/2, right? That's the same thing. So when you are asked what is the inverse sine of 1/2, the question is which angle has the sine theta equal 1/2. Anybody remember? This you have to remember your like unit circle values of sine and cosines or whatever. What do you say?
Pi over 6.
Pi over 6, she says. Yeah, I actually don't per se have these memorized, but yeah, the pi over 6 is the 30, 60, 90 triangle. So I have this little picture memorized. And this indeed is the one where the sine of that angle is 1 over 2, the opposite over the hypotenuse, right? So here the sine theta equals 1/2, and that is the 30, 60, 90. In particular, this is the 30, which is pi over 6. All right, so all that to say inverse sine of 1/2 equals pi over 6, all right? Yes?
Would you also have us say the other values? 'Cause
No.
It's just pi over 6.
Right. Yeah. So this is a good question. Inverse sine is a function whose domain and range are like so. All right. Now you could say, well, what about pi over 6 plus 2 pi? That is not a value in the range. Right. The range of this function is only minus pi over 2 to pi over 2. Now it is true, so this, I think this is worth writing down because this is something good to say. So there are other thetas with sine theta equals 1/2, right? For example, pi over 6 plus 2 pi. That one also has sine theta equals 1/2. That is like you go all the way around the circle and then another 30 degrees, all right? But we don't use those. It's because inverse sine of x gives answers, because of that graph, the domain and the range or whatever, gives answers only in this interval, minus pi over 2 to pi over 2. All right? Even if you think, yes, there are other angles that have this sign, we're not talking about those because the inverse sine function is a function. It just gives you one answer. It doesn't give you multiple answers. All right. Excellent. What about, how about inverse sine of 1? That is, what's the angle where the sine equals 1? Yeah? Pi. I think it's not pi. Sine of pi is 0. This is the shape. I'm looking for this, right? Yeah, that's pi over 2.
Oh, pi over 2.
Pi, yeah, pi is in the middle here. This is 2 pi. Yeah, this is pi over 2. Since sine of pi over 2 equals 1, right? And pi over 2 is part of that domain. I mean, pi over 2 is part of the range of the inverse sine function. Like she said, of course, there are other angles for which the sine equals 1, but they aren't the ones that we pick when I ask you what the inverse sine is. All right. Sometimes, like I said, this is sometimes written as arc sine, so I hope you won't freak out if you see it written in this way. How about the arc sine of negative 1 over root 2? This one is a little more complicated. You have to, I don't know how you think of your sines and cosine values in terms of the unit circle or whatever. When I see the root 2, I know that I'm talking about this 45, 45, 90 triangle. And the sine, so this It's not that way. It's a 1 here, and a root 2, right? So that angle in this picture is 45 degrees, otherwise known as pi over 4. How do I get a negative? Does the negative matter, or yeah?
Isn't it like we're going like backwards? Like you're not going clockwise.
If it were a negative angle, then I would measure it counterclockwise. Does that actually make the sign? Like this picture that I drew here, the sign here is 1 over root 2. Really, I want a picture where the sign is negative 1 over root 2. How can I maybe... The sign in this case is determined by this and this, right? The opposite over the hypotenuse. Really, and there's no way to make the hypotenuse negative, but you can kind of make that thing negative.
You
Yeah.
put the triangle in the fourth quadrant.
Uh-huh. Yeah, and maybe this is what you were saying at the beginning. If you make this angle go down here, so you could think of it either like that or as a negative angle like that. Now the sides would say -1 and root 2. So actually, this is the appropriate angle to be using. I think maybe that's what you were saying.
Yeah.
Which way should I say it? Should I say, so this angle all the way around would be something like 7 pi over 4? Or this would be negative pi over 4? Which one should I say? Negative pi, yeah, actually, that's the only correct way to say it is negative pi over 4. Why do you choose that rather than the other one?
It's in the range.
Yeah, because negative pi over 4 is actually in the range, and the other way around, 7 pi over 4, is not part of the range. So I will just emphasize not 7 pi over 4, even though we typically think of those as representing the same angle, and they do represent the same angle, but in terms of a function which has a specific real number answer, they are certainly not the same real number. You know, negative pi over 4 is a different number from 7 pi over 4. It's not this one since that's outside the range. So these are sort of little details that, you know, when you're using the inverse trig functions, usually this stuff doesn't matter, but sometimes it does matter, and you have to be aware that this is sort of a weird function. All right, great. Let's just talk about some basic facts about the arc sine or the inverse sine function. So since they are inverses, and this also has some bit of technicalities, but something that everybody knows about inverses, you can do this kind of f of f inverse of x equals x, right? That is always true of an inverse function. So something like that will be true for the sine and the inverse sine, although there is some amount of technicality about it, but I'll just write that first of all. Sine of inverse sine of x equals x. This is true only for certain values of x. This is true when x is in the domain, that is to say -1 to 1. In order for this to make sense, x has to be part of the domain of this first function you're plugging it into, which is inverse sine. And so this formula is true when x is in the domain -1 to 1. If you try to plug in, say, 2 here, actually, if you did this on your calculator, you would get an error if you said, what's inverse sine of 2? So this is, basically, this is always true no matter what x is, as long as it makes sense to plug it into there. And then the other way around is true also, but this is where it gets a little more complicated. So this is also true, but this is only true when sine of x is in the appropriate range, or when sine of x is in the appropriate domain to be plugged in here. This is true when x is in -pi/2 to pi/2. If x is outside of that, of this domain, then you will still be able to plug it in here and do the inverse, but you won't get the answer what you started with. For instance, if I begin with x equaling 7 pi/4, I plug it in here and then take the inverse, I'll end up with -pi/4 instead of 7 pi/4. So some weird stuff will happen if x is outside of this domain. And that you just have to keep in mind. All right. We got about 10 minutes left. That's enough for one last property of these inverse trig functions. We can determine, I will say, weird stuff like, what is cosine of inverse sine of x? Obviously, if you use sine both times, sine of inverse sine of x, that equals x. But what if I do cosine of inverse sine of x? My knee-jerk reaction would be, I don't know, that's not anything, or you can't simplify that. But actually, you can simplify this. There's kind of a formula for this, which I wouldn't expect you to memorize, but I would expect you to be able to figure out what it is. All right? And the way to do this is, of course, inverse sine of x is the angle which gives you sine theta equals x, right? That's the meaning of inverse sine of x. It's the angle theta, which gives you sine of theta equals x. And we can actually draw that on a triangle for an example like this. This is sort of not to scale, but if this is supposed to be my angle theta, and I want the sine of theta to equal x. Now, there are many ways that that could happen, but the sine, of course, is the opposite over the hypotenuse. And if I want that to equal x, the simplest way to do that is to make the opposite side x and the hypotenuse 1, right? So this is because the sine of theta is supposed to be the opposite over the hypotenuse, op over hyp. And if I want it to be x, the most sensible way to do that is to make the op x and the hyp 1, right? Because I want op over hyp to be x over 1, which is x. But now, what's the question originally being asked here? What is cosine of inverse sine of x? This here, this would be cosine of theta, right? And actually, we can, using the diagram that I drew, you can actually figure out what the cosine of that theta is. The cosine, of course, is adjacent over hypotenuse. And I didn't put a label for the adjacent, but how could you figure out what's the adjacent side here? You don't have to tell me the answer, but get me started at least. How would you figure that out? You can figure that out from this triangle, yeah?
You'd use like Pythagorean?
Yeah, you can use the Pythagorean theorem. This is a right triangle, of course. And so the way that these sides go, maybe I'll just temporarily call that A. It must be that a squared plus x squared equals 1. And then you can solve that for A, right? I would subtract the x squared first. 1 minus x squared. And then square root on both sides. I always think in the back of my mind, do I need to consider plus or minus? But I answer to myself, no, because this is just a distance, so I don't care about the negative version of that. All right? And so my triangle actually looks like this. Root 1 minus x squared, x, and 1. And here's theta, right? And so what is the cosine of theta? It is the adjacent over hypotenuse, which is 1 over root 1 minus x squared. And that actually is the answer to this original question that I was asking. What is cosine of inverse sine of x? It is that which I wrote at the very end in the box. Because this angle theta is the inverse sine of x. And then all this business, you can find the cosine of theta. So the conclusion is this is actually a general formula, which is always true if the numbers are appropriate for the domain. Cosine of inverse sine of x equals this. Now, like I said, I would not expect you to have this formula memorized, but on a quiz or a test or something, I might ask you to come up with this formula. And the way you do it is by drawing the triangle, like I just did. This is a formula for cosine of the inverse sine of x. Did I do something wrong? Everybody's
You
saying.
did the other way around.
It's not 1 over. Yeah, sorry. There's whispers, which usually means I wrote something wrong. Yeah, it's adjacent over hypotenuse. This, I guess, is the secant. So it is true. Secant of inverse sine is that. Not what I wanted. Sorry about that. So this is just this. Not the reciprocal of that. Because it's the cosine is adjacent over hypotenuse. Thank you for that. Sorry about that. So this is like so. All right, cosine of inverse sine. I want to do also tangent of inverse sine, but maybe we'll start with that next time. Oh no, actually, it follows immediately. We can just say it all together now. What is tan of inverse sine? You go through the diagram like we did, but actually you don't have to do anything fancy because it's the same diagram. This theta here represents inverse sine of x, right? And so we can use the same diagram, just doing the tangent instead of the cosine. What would that say? I'm looking at the same triangle here, just doing the tangent, yeah.
Root 1 minus x squared over x. Oh wait, no, the other way, sorry.
I'm beginning to doubt even myself. Yeah, it's the
X
opposite over adjacent. So,
It's x over.
yeah. Over here, using opposite over adjacent will be x over that. There you go. These are formulas for cosine and tangent of the inverse sine. All right. That's how we do it. I wanted you all to try to do similar things for the inverse cosine, but we'll start off with that next time. I don't think there's enough time for that. All right, let me know if you have questions about the homework. I would be happy to discuss. See you all tomorrow.